So a simple harmonic oscillator, those three words are not arbitrarily chosen. They each add something to the context of what an oscillator is. So I want to start by kind of defining what these words are here. So there's two modifiers to the word oscillator here. Oscillators are anything that travel in a repeated path. That's an oscillator, anything that travels in a path that repeats. So we could say that you going to school is oscillations if you go to school and then go home the same way every time. Right? That'd be an oscillation because your movement is a repeated pattern. And that pattern is something that is maybe or maybe not predictable, but it's a repeated pattern. The word harmonic means that it takes the same amount of time to repeat. That's what the word harmonic means. So a harmonic oscillator is something that repeats its motion in a regular way, taking the same amount of time. Okay, so harmonic means that it takes the same amount of time to oscillate. Simple adds another layer. A simple harmonic oscillator is an oscillator whose motion can be modeled with a sine or a cosine function. Yep.
Like a fan?
What do you mean a fan? Like an oscillating fan?
I think just a fan spinning and counting a simple harmonic oscillator.
Something that goes in a circle can be considered a simple harmonic oscillator if it fits those three functions. So the thing that's going in the circle would have to do so in regular intervals in such a way that its motion can be modeled as a sine or a cosine function. So just traveling in a circle wouldn't be enough. But if I wanted to look at, say, just the x-coordinate of an object traveling in a circle, then yes, that could be modeled using a sine or a cosine function. In fact, that's what you guys did when you were doing the unit circle. You were using something that was traveling in a circular path, but you were focusing on the x-coordinate and the y-coordinate of that circular path. Right? Isn't that what you did in pre-calc? For all of that stuff, it was y equals sine and x equals cosine the whole time. But you were dealing with the unit circle. So that connection between circular motion and simple harmonic motion is made. And we're going to see a bit of a video about that on Monday. So the general form of, say, a cosine function would be something like this, or for a sine function would be something like that. Do you also remember that you could write it like this? Is this something you remember? Because if you do, then I'm going to count on you knowing it. If you don't, then I will talk about it. Because there's also, you can add this. And these are all the ways, I mean, this is what the generic form of a sine function looks like. Do you remember what all the pieces represent? Okay, so raise your hand if you don't remember what all the pieces represent. All right. It could just be that you guys haven't gotten here in pre-calc, but I thought this was a pre-calc topic. Is it?
Yeah.
So have you just not reached it yet? Okay. So I'll talk about what each piece is, but we're really going to focus just on this one for the most part. But let's deal with what these pieces are. First, this one scales the function, right? Sine can only go between 1 and -1. But this is what scales it for what we're dealing with. So for example, the spring bouncing up and down, it's only bouncing a couple of centimeters. This takes and scales it for the centimeters of bouncing that's actually taking place. Let me say this again. What's the biggest the sine function can be? You guys all know it's 1, right? What's the smallest the sine function can be? -1. So the sine function goes between 1 and -1. X0 represents how big the bounces are. The biggest bounce is only a couple of centimeters above and a couple of centimeters below. So X0 scales it for the situation that we're observing. It's known as the amplitude of the oscillation. Amplitude is the maximum displacement of your oscillator. So if sine and cosine can only go between 1 and -1, the x naught multiplies it by the maximum size of your oscillation. That's what x naught means. It's the amplitude. Now, some of these other things we're not going to deal with. Like this is necessary for what we're observing right now because my detector can only see things that are in front of it. But this is going to be your offset from 0. Because I can't make the motion sensor be at 0 because it can't see anything behind it, I've offset the oscillations above it. So that's why in the graph that's up there, you'll notice that all of the parts are above 0. Right? 0 somewhere down there at the bottom. Find 0 if I can. There, so 0's here. And if I look at what I have, it looks like I'm about 30 centimeters above 0. And we know that that's probably pretty close to the range, right? Because the sensor itself has its own limited ability to see in front of it, so it starts just above 30 centimeters from where it's bouncing. That's what we saw above there. That's what we would expect. There's an offset, setting it up there above where 0 would be. Now, some of these, I'm not sure you are as good at remembering what they are. And one of them is actually very important to us, and one of them isn't. This one, do you remember the name of this one?
Phase shift?
It's the phase shift, yeah. That shifts the function left or right. Sine would start at 0 without a phase shift. Cosine would start at +1 without a phase shift. This term here determines what feature of the graph. So how close the peaks are or how far apart the peaks are. Now, our function that we're going to deal with for most of this, we're going to clean this up and only look at this. We're not going to worry about phase shifts at all. In fact, we'll very seldom even use these. But what I want you to recognize is this term and what it means. And yes, it brings the peaks closer together or spreads the peaks further apart. And we call this the angular frequency. And you guys tend to be a little like not understanding what's important and what's not. So let me try and give you something that's important here. The angular frequency has to be in radians per second. It has to be, because I'm multiplying by time, and I can only take the sine or the cosine of an angle. So the angular frequency has to be in radians per second. The offset is going to be in the same units as the amplitude. It has to be, because it's offsetting by the same thing that we're measuring for the bounce. Phase shift is going to be in radians, but we're not going to have any phase shifts. The only reason there's a phase shift right now is because the picture on the board shows a phase shift from the data I collected, because I started it randomly. The first thing I want to highlight is the top picture. The top picture represents equilibrium. I've done nothing to the system. The system is in its relaxed state. At equilibrium, net force equals 0. And I've not done anything to the spring. It's just sitting there with a mass attached. What I am going to do is I'm going to mark equilibrium for this whole paper. So this blue line represents the equilibrium position. Now, when the mass is at equilibrium, the force from the spring is 0. Do you remember Hooke's law from first semester? Can you tell me what Hooke's law is? Hooke's law states that a spring provides a force that is proportional to the displacement. That's what Hooke's law states. So in the case of this spring, when it's at equilibrium, x is 0. So the force from the spring is 0. All good so far? Simple enough? All right. I'm going to take the mass, I'm going to displace it a distance x naught from equilibrium. This is where I've pulled the thing out, I'm about to release it. This is you taking the spring mass oscillator that you had for your lab, lifting the mass up a certain amount away from equilibrium. You are establishing the amplitude. You are determining what the largest oscillation will be because you are, in a sense, applying energy to the system. By pulling the spring out, I am adding energy to the system. It should be recalled that the energy in a spring is equal to 1/2 kx squared. In this case, it's x naught squared. At the same time, I am at a point of maximum displacement. So my net force is going to equal ma, but that net force is kx naught equaling ma. Now, there's a lot to unpack here, and you need to understand the things that are important, so let me kind of point out the things that are important. X naught and A are vectors. The object has been displaced to the right and is currently experiencing an acceleration to the left. That's what Hooke's law states. In your notes, what I want to remind you about is Hooke's law is what we call a restoring force. It's attempting to restore the system to equilibrium. The spring is pulling on the mass to the left. So even at this moment, the net force has got to be this way from the spring. The spring is pulling the box to the left. Okay? This is the moment that we let go of the box, t equals 0. Okay, so we are just letting go. At this moment, the velocity of the system is 0. All good? Everybody follow along with that argument so far? What's happening? We're going to follow along with what this object is doing. I want you to pay attention to very specific variables. I'm going to tell you what we're paying attention to. We need to pay attention to position, acceleration, energy, and force, and velocity. Those 5 things. Position, acceleration, energy, force, and velocity. That's what we need to pay attention to. So, we release the box. The spring pulls on the box to the left. X naught is as big as X is going to get. So after a few moments, this becomes minus kx, which x represents whatever this distance is, something less than x naught. And that's going to equal ma. Because x is smaller, our force acting on the box is less. Right? The spring is not stretched as much, so the force on the box is less. However, there's been a force acting on the box. So the box now has a velocity to the left. The energy of this system is now in two places. We have energy still in the spring because the spring is not at equilibrium. But the box is now moving, so we have kinetic energy too. So at this moment, the velocity is no longer equal to 0. Now, the box is still accelerating. It's still getting faster, but the acceleration is less than it was because the force is less. So the force is less, the acceleration is less, but the velocity is increasing. We make it to the next step. We're at equilibrium. We're passing through the middle. At equilibrium, the net force equals 0 because x equals 0. So the acceleration equals 0. All of that's true at equilibrium. It's been speeding up all this time. But when it makes it here, the acceleration is instantaneously 0. This also means that there's no potential energy in the spring because the potential energy of the spring is 1/2 kx squared and x is 0. That means all the energy in the system is in kinetic, which means the kinetic energy must now be at a maximum. That also means that the velocity must be at a maximum. We'll need to come back to that in a minute. Now we crossed over this point. We make it to the other side. What direction is the spring pushing on the block now? To the right or to the left? Right, the spring has been compressed now. So it has to be pushing the block back. It's a restoring force. So now the spring is pushing this way on the block. The block still has a velocity this way. But because the spring is pushing to the right and the block is moving to the left, it's slowing down. It's not a surprise, right? This is what has to happen. We know eventually the block's going to come back to rest. So the velocity is getting smaller, but the force is getting bigger. We're back to having minus kx equals ma. We have an acceleration now. The energy is somewhere between something in the spring and kinetic energy. And our velocity is not 0, but x is also not 0, and a is not 0. So it's accelerating, still moving, and the energy spread out into both. During this time, it's slowing down. Wow, just a few moments ago, it was speeding up. All right, we make it here. How far over do you think I am right now when we come to rest?
Excellent.
Yep, but we're on the other side, so we make it to the other side. This is negative x naught. At this moment, the force is again at a maximum. And the acceleration is at a maximum. The acceleration is at a maximum because the force is at a maximum. But the velocity equals 0. We are stopped. All of the energy is in the form of potential. So we have these 2 points where we are instantaneously at rest. How much of an oscillation have we completed? This is half of an oscillation. So here to here is 1/4 of an oscillation. And here to here is 1/2 of an oscillation. We define the word period as the time for one oscillation. We define the word period as the time for one oscillation. So this represents 1/4 of the period, and this represents half the period. It's a whole lot. I'm going to add some stuff to this if you're all right with it. So I'm going to set this off to the side. I want to talk to you about what we're looking at in the form of data. Because we have data sitting on the other screen that shows the motion of the object, the spring mass oscillator. This is X, this is T. Our object starts at maximum displacement, and this is what its motion looks like. Which function is this, a cosine function or a sine function? This is cosine. We know it's cosine because it starts at maximum displacement. Okay? We use the cosine function to describe position. If we look at what's drawn on the right, and I'm going to try and put all this in red, this represents position 1, 2, and 3. On my graph, this is position 1, maximum displacement. This is position 2, at equilibrium. And this is position 3, maximum displacement, but in the other direction. Everybody follow that okay? Could I keep going? Because I want you to see this. This part's harder, okay? So this part, this bottom graph is velocity and time. I want to mark these same 3 places. At time equals 0, what is the velocity? Start at 0 at time 0. At point 2, can you tell me something about the velocity? Can we see that at point 2 we're at V max because we're at equilibrium? At point 3, where are we? What function would start at 0? So we're going to say that V equals V max sine omega t. Except I've done something wrong here. And I need you to see this before you leave. If the right is positive, what direction is the velocity at point 2? So I probably should have drawn this so it's below.